2, 3, dunk. Right, thanks. Shh. Okay, so we were using technology to graph the following reciprocal functions and find the equations of any asymptotes. So you probably kind of like knew roughly from this that there was a bit of a translation. What was a vertical translation by looking at that?
Oh, yeah, I think so vertical, so
up and down, yeah.
Yeah, so that would be the -2 then.
Yeah, exactly. It's based on the constant.
That's what I forgot.
Yep. So 2 units downwards, yep. And this one tells you the horizontal. Yes.
2 units to the right because it's the opposite side. I mean,
Yeah.
1 unit to the
1 unit to the right, yep. Exactly. When it's horizontal, it's the opposite to what you've got here. So notice that normally the asymptotes would have been x equals 0, y equals 0. But as a result of the horizontal translation, it's moved 1 unit to the right, so the asymptote's now x equals 1. And the result of the vertical translation, it's moved 2 units down, so the horizontal asymptote is y equals -2. And we kind of graphed it on the calculator. Where is it? Yeah, back here we go. Yep, so we did a little graphy graph as well. And to find the asymptote, Grace reminded us that you go onto table. So you go second table. And when we did that, it had an error thing. Error tells you that the vertical asymptote's at x equals 1. And then to find the horizontal one, you kind of just need to trace. But if you've got the equation, you can use the equation to sort of help you find out where the horizontal one is. Or you can kind of trace and sort of see, is it getting closer and closer to -2 to confirm it. So the trace button helps you a bit there. And so we've got another one that we need to graph now. Coming down. Yeah. How is it a reciprocal? Because it's like 1 over, the x is in the denominator. And the top is like a constant. So if the top is a constant, so the numerator is a constant, and the denominator is kind of like a polynomial. So it could be kind of like, x, it could be x minus 1. It could to some extent be x squared as well. So you could have a polynomial on the bottom as well. So generally, the numerator is a constant. And the denominator is a polynomial. Like your polynomials are like quadratics, cubics, quintics, quartics. Basically, where you've got like x squareds, x cubes, that kind of thing. The denominator is a polynomial. The polynomials are kind of like quadratics, cubics, quartics, quintics. Where you've got like x to the power of something. That's what makes it a reciprocal function. Because the numerator is a constant and the denominator is a polynomial. Because remember, a reciprocal, so a regular basic linear function is x. What would be the reciprocal of x?
X to the -1.
Yep, x to the -1. Yeah, and x to the -1 equals 1 over x. So do you see how, like, when it's in the form of a constant over an x kind of thing?
Oh, so that's how it's a reciprocal.
Yeah. That's why it's called a reciprocal function, because it's like the basic general function is like a linear function, y equals x, and the reciprocal of that would be x to the -1, which is the same thing as 1 over x. So that's why it's a reciprocal. Why it's called a reciprocal function when it's like 1 over x something. That's how it got its little name. Reciprocal functions, and they're pretty crazy, the old reciprocal functions, because you get the asymptotes and these weird curves and asymptotic behavior where it rises up rapidly. Down below we still have down below we still have another kind of reciprocal function, but what kind of polynomials on the bottom, on the denominator? Parabola, yeah, quadratic, that's it, yep. So it's got a different kind of polynomial on the bottom. So same thing, we've got a constant on the top. You don't need to write this if it's going to put you off notes or anything by having this written there again. So constant, which is 1, could be a different number, could be 3, could be anything. And we have a polynomial. In this case, a polynomial is a quadratic. Yeah. It's a quadratic system. So you'll still get your asymptotic kind of behavior, but the fact it's a quadratic in the denominator means the graph's going to look a little bit different. There might be a bit of symmetry going on. Oh my goodness, how did that happen? Here we go. So let's move that over here and let's do a little sketch. So get your little graphing calculators out, clear the other one you've got. And then you might need to make your nice little fraction, like you mentioned, alpha y equals n/d, like Chiesa reminded us. 1 over the thingamajiggy. Where's my x squared? Minus 2x minus 3.
Are you singing this earlier?
No.
Oh.
There. So always have a little look at it afterwards to see did you type everything in right. And then hopefully get a crazy looking graph. So my window settings are -10 to 10 and -10 to 10. Crazy graph. So do a little vague sketch of it. How many vertical asymptotes do you think it has? 2, yeah. And why do you think the fact that it's a quadratic on the bottom gives rise to 2 vertical asymptotes? Yeah, because it's a square, and you could factorize this quadratic and solve it. Because if you remember, like the way you find the vertical asymptotes is you set the denominator equal to 0, and then solve it. Yeah, because remember the double bracket. We'll do that in a little bit. I'll just take a little sketch. So we'll do a basic sketch, and I'll take a little snippet of it and paste it in. Craziness. Crazy graphs going on here. Yeah, so a quick way to get that window setting that I've got, -10 to 10, is to go do standard. Do standard the quick way. Let's get into the habit of putting that x.
I'm actually done with this calculator. I just can't.
Is that working? Is it
Yeah.
working for you? Is it because of the fraction part?
I think so.
So we'll draw in our little asymptotes. You can probably ever guess what they are, but the way we can find out for sure what they are is we can solve the quadratic on the bottom. So x squared minus 2x minus 3 equals 0. So remember you set the denominator equal to 0, and if you're to put it into double bracket form, remember we practice the quadratic algebra, what's two numbers that multiply to give -3 and add to give -2?
-3 plus 1.
Oh no, -3 and +1. So we've got two solutions. So what's the solution if we just set the first bracket equal to 0? X equals 3, yeah? And the other one, Owen, would be the solution to this one? Close? -1, did you? -1. So that's how you find the asymptotes again. Just a reminder, you set the denominator equal to 0, and you solve, and that's found our two vertical asymptotes. So we've got x equals -1 here, and x equals 3 here. So that's where those came from. They seem to have a horizontal asymptote. And again, like remember, we can always, I forgot to mention that we can always trace on here as well. I mean, we can go second table. Second table could also just remind us where the asymptotes are. See, we've got an error at x equals 3. If we scroll up, we should have an error at x equals -1. So that's confirmed it for us. And then we could probably have a little vague idea. Anyone want to guess? Normally for something like this, the horizontal asymptote would just be at x equals 0. But there's been a bit of a translation. Can anyone see what the translation is? A vertical one?
Vertical translation?
Yeah.
Compared plus 1.
+1, yeah. So where do you think our horizontal asymptote is going to be?
Horizontal?
Yeah.
Why?
Yeah, because it's shifted up. Normally a horizontal asymptote just for this regular kind of reciprocal function would be at y equals 0.
Yes.
But because of the +1, it's shifted up 1 unit. And the only way you could really check that by graphing is kind of like just trace along and see how, no, for this one, this part isn't. I'm not on there. Get back on there. Okay, that's better. Okay, so now see how it's getting closer and closer, 0.75. and so on. It's getting closer and closer. And same thing here. It'll jump on to the next one, getting closer and closer to 1. Yeah, it's a big whole one. Yeah, because this, when I'm tracing, I won't ever get to the asymptote, a horizontal one that is, but I will get closer and closer to it. So you kind of use a bit of the equation to work it out, and you also kind of just have a little check on the graph as well. Because if suddenly like it was getting closer and closer, it did cross 1, then you knew, oh, it's not 1. I did something wrong. Because then if the graph does actually cut, like, you know, a value of 1 would pop up, then you know, oh, maybe it's not 1, maybe it's 0. But we know it should be 1 anyway because of the +1. Everything shifted up 1 unit. Yes, Krista.
So horizontal asymptotes have to be horizontal.
No, they could be a fraction. Like if we had +0.5 here, so if we had +0.5 here, then it would have just everything would have shifted up 0.5. So the asymptote would be at 0.5. Yeah. Yeah, they can be fractions as well, decimals. Let's do now a little horizontal asymptote. There it is, y equals 1. With a vertical shift. So it's like 1 unit. So it's basically upwards. So that's how we end up with the horizontal asymptote. Kind of being around there. That's for basic reciprocal functions. Oh dear, how'd that happen? Any questions about that, or anyone still writing it down? Katie, you've got that stuff? Okay. Here we go. Okay, on to the next phase. So reciprocal functions are nice kind of basic versions of rational functions. So reciprocal functions, they have this asymptotic behavior. They have a polynomial on the denominator. Guys, pay attention, please. This is getting a bit tricky now. Rational functions, something kind of new. Reciprocal functions you've seen a bit. Rational functions might just be that next step further. So if they're going to be something a bit broader. So recap. Just a little bit, not much, not too difficult. Okay, so recap. The general form. So these relate very well to reciprocal functions. That's why I'll put them in the reciprocal function topic. So the general form of a reciprocal function can be written as y equals, or fx equals, something over x. Yeah, k over x, yeah. So where k is a constant. Just a number. And the bottom x could be any kind of polynomial, like it could be x minus 1, it could be x squared plus 3 plus 4, x cubed, that kind of stuff. Yeah?
These pages really have you messed up.
Oh yeah, so you'll notice that I've replaced your page 41 and 42. I'll just pause. Alright, so the general form of a reciprocal function can be written as this. So we've got k is just a constant. The denominator can be any kind of polynomial. Oh, which I was meant to say then here. So from the past few pages and the equation above, we know that the reciprocal functions are in the form of a fraction, whereby the numerator is a something and the denominator is a something. Constant, yep, and the denominator is a polynomial, yeah. So not restricted to being a linear function in the denominator. It could be a quadratic, it could be a quadratic, it could be a cubic. So like polynomials, meaning like could be quadratic, a cubic, for example, like all that kind of stuff. It doesn't have to be a linear. So that's what. So polynomial on the bottom, constant on the top. Whereas the rational functions are similar. We call this kind of like the parent function, like of the rational functions, the most basic form of a rational function. But they can also go one step further, where their functions, they're definitely in the form of a fraction, like before. Guys, listen, this is hard stuff. So they're definitely in the form of a fraction still, but both the numerator and the denominator can be polynomials. So both the numerator and the denominator are polynomials. Yeah, so it is getting a bit more abstract and complicated.
Okay, that's just
Kavina, have you got that? Okay, because this is getting tricky, so make sure to concentrate. Rational functions are similar, but they can go one step further. They're functions in the form of a fraction, like the reciprocal. However, both the numerator and the denominator, in a way, it's more like can be polynomials. Like it could be a constant here, but both, quite often you'll find in the examples we're about to do, both the numerator and the denominator are polynomials, which makes the maths a bit more interesting.
what the miscellany?
Yeah? Like these. Here's some examples down here. Crazy functions. Not functions. Crazy functions. Yeah, they're like functions that are fractions. So they're functions. I just made that up. I made it. I just made that up. Yeah, the polynomials. So these are examples of rational functions, craziness. So see, you still got polynomials in the denominators, but you can also have polynomials in the numerators. Ugh. What kind of polynomial is this one? Quadratic.
Wait, so linear is even considered a polynomial, right?
Yeah. Oh, yeah. I know. Like normally, to be honest, it's quadratic upwards, but in this case, we'll say yeah, it can be yeah, just because it makes it just easier to communicate. So we've got a cubic, we've got a linear here, we've got a linear here. So like reciprocal functions, which can be considered like the parent function, like basically the most basic form of a rational function is a reciprocal function. So similar to them, the domains of the rational functions can be found by setting the denominator equal to 0, yep, and solving for x. Because remember the domains were something like x cannot equal 1, x cannot equal 3. Like cannot equal the asymptote.
So you can find that by making the denominator equal.
Yeah, vertical asymptotes, you just set the denominator equal to 0. Like we did with the reciprocal functions and solve for x. So solving for x to find any vertical asymptotes kind of thing. So remember the domains are basically like x cannot equal 7, x cannot equal whatever the vertical asymptotes are. So then we want you to find the vertical asymptotes in the rational functions below. You can see it. So what you do is you set the denominator equal to 0.
Settle.
And what would be, if you solve, how many asymptotes would be in that one? Would we expect? If you solve, how many solutions will there be? Only one, yeah.
Oh, you mean because if it was like a factoring of 2? Like 2 by 0.
Yeah, exactly. Like if it was a quadratic, yeah. You could possibly get to, yeah. That's right. So basically you set it, the denominator equal to 0. Here's where we got our denominator from. Set it equal to 0. Solve for x. Oh yeah, they can get negative 1, yeah. Well noticed. So then x, our denominator, our vertical asymptote would be x equals negative a half, yeah. So here I just said find the vertical asymptotes. If it was state the domain, it would be x cannot equal, x is not equal to negative a half. Because remember these are just the asymptotes. So the domain would be x is not equal to negative a half, meaning all real numbers except for the asymptotes. Same thing, let's just keep going through. So another linear. So how many asymptotes will we get for this one I'm just doing here?
Oh, that was pretty quick when you moved on to that one.
Yeah, 2, yeah, good. So what would be the asymptote as a result of this bracket?
-2.
Yeah. Yep, so 2 vertical asymptotes. So our domain for this one would be x is not equal to negative 2, x is not equal to 2. Because the asymptotes are where the function doesn't exist. But here it just asks what's the asymptotes, not what's the domain. So we just go x equals and that's it. Pretty crazy. So this is where you get to practice your factoring.
So what multiplies to adds to -1
Yeah.
and multiplies to -2.
Okay. Yep. Isabella, if we were to factor this quadratic, what would it be?
It'd be, oh god.
How do we?
It's off the top.
Yep. Try to focus and don't get distracted, please. Yep. Yes.
-2 and 1.
-2 and 1. Yep. That's right. -2. And why is it -2 and +1?
Because -2 times 1 is -2, and -2 plus 1 is -1.
Yeah. Exactly. Yeah. That's it. Good memory. So this is good because it's practicing our quadratic algebra, which is kind of implied in this unit. So then our two asymptotes. What would be our two asymptotes? Yeah, 2 and -1. Let's go up and look at here.
Oh, that's seven words in the word.
What one?
Didn't you know they went from fun in Spanish?
So do you remember this kind of quadratic? It's a difference of squares. Difference of squares, yeah. So just remember what would go into the brackets. So difference of squares. Difference of squares, so the square root of that is x, square root of the other one, negative 4 is 2. Plus and minus 2 means that you've got 2x minus 2x, which is why the x term's gone. So our two asymptotes will be, yeah, -2 and 2. So it's because they're quadratics, that's why we're getting two vertical asymptotes. So I only seem to put linear and quadratic ones here, cubic ones. A bit more complicated. So again, we've got two asymptotes at this point.
Oh, x equals 0 and x equals -1.
Yeah, good.
Go, Grace girl.
Yeah, sometimes people get thrown when that happens. So it's still a quadratic, so it's still got 2. It's just been factorised for you. So if it was x squared minus x, you would have to factorise it first and then realise that you've got your two vertical asymptotes. Like that and that. Here we go. Okay, so horizontal asymptotes. Finding the vertical asymptotes is really easy, like you just do what we did. Finding the horizontal asymptotes, there's all these tricks and strange things going on. So this might be quite new for you. Horizontal asymptotes of rational functions are found by asking the question, what happens to the function as x grows very large, like going to the right, goes to infinity, and to the left, as x gets really, really small, like -10,000 and +10,000? What's happening to the function as the x gets bigger and bigger and bigger in both directions, the positive and the negative? So finding these is a different kind of mathematical exercise to finding the vertical ones. The vertical ones are easy to find than you might be used to. First, when x is very large, the constant terms, so when x gets bigger and bigger and bigger, like into the millions,
Getting larger if it's going into negative, getting smaller.
They're getting larger in both directions.
Yeah, that's a good point, yeah.
Is that the opposite of larger?
Yeah,
because you said the signs are opposite.
more negative, maybe?
Man, why can't it just be if it goes right?
A larger negative quantity?
Isn't that makes me happy?
Further negative. Maybe we say further negative.
Scale, you can only go one direction for larger. And since we've already defined larger as getting larger in positive numbers, and the more negative you get, it would have to be smaller.
Yeah, in the sense it's getting infinitely smaller, isn't it? Yeah.
I want to see that shaping up.
Yeah, that's a good point. So maybe, how could we phrase it then? Larger in the positive direction and further
Just
negative.
more negative and more positive.
More negative and more positive. Yeah, that makes sense. That covers everything. Meaning like further out this way on the axis. Like further out. Yeah, so notice that, and the whole thing is when x is very large, the constant terms will hardly matter at all. So in a way we cancel them out. So imagine when x gets really, 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 really big in that way or that way, left and right, these things will become almost like they don't matter. Like imagine x is 1,000,000. Do you think 1,000,000 plus 2 over 1,000,000 minus 1 Do you think the +2 and the -1 matters anymore?
No.
No, it doesn't, yeah. So what we can do is we can strike them out. So by striking them out, we can say, pretend they're not there. This is just for the purpose of finding the horizontal asymptote. Like not doing anything else, just for the purpose of finding the horizontal asymptote. So that's, yeah?
X over X is just 1.
Yeah, exactly. So that will mean our horizontal asymptote, by the way, is going to be 1.
Oh,
Yeah.
boy, you're smart, girl.
Yeah, so you've gone to where the horizontal asymptote is.
You want us to just do like 1 million over 1 million?
Yeah, just like pretend they're not there. Which
No,
will
I'm
be?
talking about
Oh, it's same in theory. What you do is like you don't bother to substitute it in, but you say, okay, if they were really large, then these wouldn't be important anymore. We're not quite done. We've still got a few things to fill in. Yes, Krista?
So we cancel off the signs as well. The signs go with
Yeah, you're right. Yeah, so the signs don't matter either. So now we just think of it as being just x over x. To see if the constant terms don't matter, because imagine we've subbed in a really large value for x, the constant terms won't really matter anymore. And therefore you get x over x, and x divided by x cancels to 1. Yep. So the horizontal asymptote will be y equals 1. So as we said, it's not exact. This is not an exact math. It's just a method we use for finding the asymptote, horizontal asymptote, if we don't have a calculator or something to trace with. If we have a calculator to trace with, we can always try that. But yeah, so that's why it's a bit weird, because it's not an exact mathematics. Like we're kind of saying, oh, they're not important anymore, so let's get rid of them. But really the function is still this. It's just for the purpose of finding its asymptote. It's horizontal asymptote. So it is complicated and weird finding horizontal asymptotes. But this is just one method. Like, there's all sorts of other weird methods as well. Here's another example. So same thing. This is the original function here. What we do is we imagine that x is a huge number, positive or negative, but mainly we'll think positive in this case. So therefore, if x was 1,000,000, then 2 and -1 doesn't count. It's not important, because 3 times 1,000,000 over 1,000,000 is that's the bigger part of the number. Those things probably wouldn't even register on your calculator. Those things coming up, maybe it might get 0.00000 something. So then, when these kind of are struck out, then you can rewrite it as 3x over x. And what does that simplify to? 3. Yep. So our horizontal asymptote in this function will be
3.
3. Yeah, y equals 3. So it's just another method.
What is it? What? I'm looking at your little thing. Every time you do this, a kitten dies.
Yeah, so I've put this in here because there might be a bit of cancelling down required in this one. And remember, like sometimes people are in the habit of cancelling down stuff like that. But instead, like it has to be more like x times by x minus 1 or something over x. Then you can cancel it down. When x is a factor of the entire numerator and the entire denominator, then you can cancel it down.
So how does a kitten die? That's
So-
just me.
And so notice x is not a factor of all 3 terms. All terms. Yeah. So that's why it can't be cancelled down.
It's not that the kitten.
The kitten, that's just meant to make you feel bad. Like it's meant to be something so that you feel so bad you don't do it.
Oh, got you. So then I don't cook.
Yeah. For year 11s, we always called it killing a kitten. And they naturally say, oh, I killed a kitten again.
What?
Yeah. And one of them would say, I kill kittens all the time. And you didn't realize what she was saying. Is it about that?
I think.
Yeah, it should make you do some emotional memory so you won't do it. There's a whole series of them. There's a whole website with these kind of things on there.
I love this one.
Okay,
This is the only person happy.
so this is a hard one. Notice that we've got a quadratic on a quadratic this time. Yeah. And so same thing, the constants don't matter. So we strike them out. So it's just one little constant there. And when you do that, now I'm about to factorize. So so maybe I might do that first.
Let's pay attention to tomatoes.
So
Take out 2x.
yeah, so we're going to try not to kill a kitten. So we're going to maybe factorize the top first and factorize the bottom next. That might be a good idea. Actually, to be honest, you can take out 2x really, couldn't you?
You can.
Yeah. I'll kind of take out 2x if you want, but I'm just doing it.
No, take out 2x.
I want to write it again. Take out 2x and see if we get the same answer. You take out 2x and we'll see. We should hopefully.
Why can you take out 2x?
Because 2x is a factor of the numerator and 2x is a factor of the denominator.
I'll just keep it then.
Yeah, I'll just keep it as x. The main thing I'm trying to do here is cancel down an x. So in my case, I'll get 2x plus 2. So the,
Plus 4 subtract 4.
yeah.
Oh, yeah.
So see how x is a factor of the numerator and the denominator, so we can cancel down. We haven't killed a kitten.
Okay, I'm gonna do yoga in this minute because you're almost got trigonometry out.
We didn't kill a kitten. And it doesn't matter if you didn't take out the 2x yet, because it's going to cancel down. The two parts going to cancel down later anyway. Yeah, you could go straight
Did
to
you
it.
do 2x in the card, Kenny?
Yeah,
You put 2x in the card?
I was thinking about it.
yeah, you can totally do that, because the 2 and the 4 are eventually going to cancel out anyway, so you can just cancel them out earlier if you want. So then we've got 2, so now we've got a new looking function. We've got 2x plus 2
This looks like a food chain.
over 4x minus 4. And see again, we've got constants. So they are again, as x becomes a really, really large number, they're not become important, so we can strike them out.
Oh.
So 2x over 4x, what does that simplify to?
A half x.
Close?
Half.
A half, yeah, good. A half. And I am a bit lazy, I should have been writing fx equals. So sorry, I'm going to fill in quickly fx equals. F of x equals. I'm just rewriting this with f of x equals in the front to be more consistent. It's okay if you don't. Look back on. And I should have had f of x equals. So what would be our asymptote in this case?
A half.
A half, yeah. So I forgot to write it here. So our horizontal asymptote is y equals a half. It's the same thing as if you wrote fx equals a half. So our horizontal asymptote is y equals a half. So a bit more complicated when you've got a quadratic over a quadratic. The previous ones we had a linear over a linear. Or the ones above. So they're a bit easier. So what we had to do was like cancel out any constants to begin with.
Yeah.
Take out x. You could have, if you took out 2x as common, you still need to end up with a half. So that would have been fine to do that. And then cancel out constants again, and then you get your asymptote. A lot of messing around to get your asymptote. If you can graph the thing, that's a really good idea, because this is a bit complicated, so things could go wrong. So graphing is a good way to check it. So notice that in the above examples, the degree of the numerator is the same as the degree of the denominator. You know what I mean by the degree of a polynomial?
No.
Oh, okay. I'll let you know. Degree is the highest power of x. So what's the highest power of x in the top?
2.
2, yeah. So these are polynomials of degree 2. So let's see if we can write that in. So polynomials of degree 2. What would be the degree of the polynomial above that?
4.
Yeah, you're probably wondering which one am I talking about. Talking about this one. What would be the degree of those two polynomials?
1.
1, yeah. It's like, what is the highest power of x?
Exactly. It's not there, so you automatically put it to 1.
Oh,
You have no
power,
power. Like exponent.
Yeah, exactly. Yeah, you see that.
Something like coefficient.
So it's all because in here we talked about the thing called the degree of the polynomial. the degree, and you don't really have much space to write something about that, maybe in the line just underneath this sentence. So the degree of a polynomial is the highest power of x that you see. So if it's a cubic, then the degree of that polynomial is 3. So the degree of a polynomial is the highest power of x.
You have Slanted? Yes.
Yeah, so that's why these two are polynomials of degree 2. The above ones are polynomials of degree 1. If it's a cubic, it's a polynomial of degree 3. So notice that in the above examples, I've given you, this is the most basic kind of one for finding horizontal asymptotes, where the degree of the polynomial in the numerator is the same as the degree on the bottom. And then you'll notice in the examples above that was a linear over a linear, and I've just done a quadratic over a quadratic. They're the easiest ones to get. On the next page, I have to tell you about ones where maybe the degree on the top is less than the degree on the bottom, and vice versa. Yeah, that's on the next pages. Okay, anyway. So on the next page is when we start to talk about when the degree of the numerator is not the same as the degree in the denominator. Is anyone writing that still? Oh, looks like some people are writing. Yeah, just give you a moment to finish that. Am I recording? Yes, I am. Good. Here we go. So here we go. Some examples of horizontal asymptotes when the degree of the denominator is larger. So see what I mean by that? We've got a linear on the numerator and a quadratic in the denominator. So in these examples, and see I've got a quadratic and then a cubic in the denominator. So these are examples when the degree of the polynomial in the denominator is larger than the one in the numerator. What do we do? So this means that as x grows, the denominator will grow faster than the numerator. Because if you plug in 1,000,000, if you go from plugging in 100 into here to suddenly plugging in 1,000,000, you'll notice that the denominator has grown much more rapidly than the numerator has. Does that make sense? If you plug in 100 for x, and then compare that to if you plugged in 1,000,000 for x, when you plug in 1,000,000, the denominator has grown much faster than the numerator has. And by analogy, with a function 1 over x, the basic reciprocal function, the horizontal asymptote will be at y equals 0. So these ones are easy. So basically, if the denominator is larger, the degree in the denominator is larger than that, you just end up with y equals 0 as your asymptote. Oh yes, so what it's meant to be is, so same thing, like in a way, like kind of these constants don't really matter as x gets larger, infinitely larger. So then you'll get your x over x squared. And what does x over x squared can be cancelled down? What does that simplify to? 1 over x, yeah, which is the reciprocal function. Oops, I just meant to write the slash again. It's already there. So see that thing. So see just the basic reciprocal function. And what's the horizontal asymptote of the basic reciprocal function? Is y equals 0. The basic reciprocal function has x equals 0, y equals 0. But obviously our x will be different, that's the difference of squares. So our horizontal asymptote will be y equals 0. Horizontal asymptote. So the horizontal asymptote is y equals 0, because when you've got this, it kind of cancels down to 1 over x when you do our cancelling down business. So it is not too hard when the denominator has a higher degree than the numerator. When it's the opposite, it's a little bit more tricky.
Miss Marie, I don't get how you went from 1 over x to that equals 0.
Oh yeah, so it's all because of this. The basic reciprocal function has a always has the horizontal asymptote at y equals 0. Because remember back to our lessons on reciprocal functions, like 1 over x is just at x equals 0, y equals 0. So when it cancels down, it becomes like a basic reciprocal function.
Oh, so
we should probably write it
yeah,
down.
can you make a note?
Yeah. So it cancels to the basic reciprocal functions. The basic reciprocal functions. horizontal asymptote. So it cancels. Yes. It cancels to be the basic reciprocal function, which is 1 over x, with horizontal, and the basic reciprocal function has a horizontal asymptote at y equals 0. We still did that whole thing, like, you know, strike out. So we did the strike out. Strike out the constant. And as I said, the only reason why we strike out the constants and do all this cancelling down is purely for the purpose of finding the horizontal asymptote. If you're not needed to find it, you're not required to find it, then you wouldn't bother to do anything here.
Okay, I think I've got the homework.
Yeah, it's a bit really this one. And we've got a slightly more complicated one down below too. It cancels to be the basic reciprocal function. That one too. So now we've got what polynomial do we have in the numerator? What kind of polynomial is that? Quadratic. What kind is that one? The cubic, yeah. Oh, out of interest, the one above, this one here, what would be its horizontal, its vertical asymptotes?
-1 and 1.
Yeah. How do you get that?
Difference of 2 squares.
Yep. Set it equal to 0, and yeah, and it's difference of 2 squares. Yep. X minus 1, x plus 1 in brackets, so x equals 1, x equals -1. Yeah, so it would have a horizontal asymptote, just reminding you of the vertical asymptote stuff. Horizontal asymptote at y equals 0, and a vertical asymptote at -1 and +1. That's what that one would have, the top one. Yeah, it's irritating. I would find this irritating. It's just irritating and strange. Finding the vertical asymptotes is pretty easy, to be honest, really. But it's the horizontal stuff. It's just weird. And it's annoying because it's not an exact maths. Like, in maths, you normally couldn't cancel down these constants, could you? That's not allowed. That's killing a kitten almost. So that's why it's frustrating, because it's not an exact maths. It's just the best method we can find for now for finding these asymptotes, if you don't have a graphing calculator. Yeah, so they're pretty... This is pretty bad. In high level, they probably do it a fair bit. They probably have to do these kind of rational functions a lot. But we kind of need to be aware of them and potentially be able to do them. Not as much as them, though. Okay, yeah, so we've got a quadratic over a cubic. We strike. What do I do next? What do I strike out?
The constant
one.
Yeah, plus 1. So then it's already been cancelled down for you. This one, it takes ages to write, so I filled in most of it for you. 3x. So maybe we can fill in a little middle step here to see, like, just showing you why we didn't kill a kitten, going from here to here. We'll cancel down x, because this one here is the same as x, 3x plus 2 over x cubed. Yeah, that doesn't, yeah. So see how we can cancel down an x? We can cancel down an x from here and an x from here to make that x squared. So that's how we get 3x plus 2 over x squared there. Just showing you that we didn't kill a kitten. So we cancel down x's. And then, again, like, we can strike out the constants again. So we did a strike out here. Then we cancel down x's and we did a strike out again. And then you get 3x over x squared. So 3x over x squared, would you agree that the x's cancel down?
Yes, and that's the basic reciprocal function,
Yeah.
which is why the asymptote is 0.
Yeah, good. Again, it's just y equals 0 again. Because remember, the basic reciprocal function just has k over x. Like, you know, it could be a constant. So long as it's a constant over x, it'll have a horizontal asymptote at y equals 0. So that's our horizontal asymptote there. So again, it's just a basic reciprocal function again. Basic reciprocal function. And basic reciprocal functions have asymptotes, horizontal asymptotes at y equals 0. Cubics, you could potentially get 3 solutions, or maybe you can get 2 solutions. That might only get you 2 solutions, that one. Yeah, sometimes you could get no solutions, because remember, like, it's possible for a quadratic or a cube, like, to have no solutions. Do you remember that?
Yes.
Quadratics could have no solutions, and I'm just pointing out, like, if it has no solutions, it means it's got no x-intercepts. Like, that could have no solutions. That one could have no solutions. So it's possible for a quadratic to have two solutions, like that one, like two x-intercepts. It could have one solution, like this one, or it could have none. So there might be the case where some weird rational functions turn out not to have vertical asymptotes, because when you try to factorize the denominator, you end up with no solution. And that comes up on a later page. So that's not too bad. This one is the weirdest one. Horizontal asymptotes when the degree in the numerator is larger. So it does this. I've got saved the weirdest for last. So here you see the degree in the denominator was larger. That's fine. That was pretty straight up, because it just cancelled to a basic reciprocal function, and then it's just y equals 0. When the denominator, when the one degree in the numerator is larger, you can get weird asymptotes. So the kinds you can get slanted, like lines that are kind of diagonal instead, slanted or curved asymptotes. You might not come across these very often in this course, but we just still want to make you aware of them. It did come up on a CIE exam recently. There was a CIE exam where there was a graph, and it turned out its asymptote was slanted, and I thought, I didn't think that was in this course. But maybe they just expected them to work it out by graphing and looking at it. They weren't expected to know the maths behind it. It was on a recent CIE exam. I thought, that's crazy. Okay, so got 10 minutes. This one, as I said, is weird. So you can get slanted or curved asymptotes when the degree in the numerator is larger than the degree in the denominator, like the opposite. So I know this is kind of taxing, but try to make yourself listen. Thank you. Am I recording? Good, yeah. So this means that as x grows, the numerator grows faster than the denominator. Whereas because if you plug in 100, then that number is big, that number is big, but then you suddenly plug in 1,000,000, this number is way bigger than that number, because of the fact that it would be 1,000,000 squared over 1,000,000. So as x gets larger, the numerator will grow faster than the denominator. So what would otherwise normally be a horizontal asymptote, in these cases, can become a slanted line, like a diagonal line instead, or another curve, could look kind of like a quadratic kind of like asymptote. In these cases, yeah, I just said that, such as a parabola. To find the equation of such an asymptote, we have to do a thing called polynomial long division, which I didn't think was really in your course, but we'll do it anyway. This is a bit more at high level, but again, like, you know, you never know if something like this might suddenly pop up on an exam. Yeah, polynomial long division too. So don't worry, I've filled in the example for you. We'll just kind of like, you know, talk you through it. I could teach it to you via polynomial long division. Look, it's the same maths as year 7, grade 6 long division. I mean, this tends to be the only time you'll ever need it.
Primary school, I thought he said a calculator.
Yeah, we used to teach it in like year 10 and 11, like in my old schools, but mainly because they needed it in higher level, not that they needed it in SL.
I was in year like 6, and I did it like this, and they told me not to.
And actually, it doesn't matter. Like, I can understand why they still would like not teach it, because even if you were a master at it in a younger year, like, you know, you have to learn. This is slightly different style of thinking anyway. So whether you learnt it before or not probably doesn't matter. Doesn't even help you. Okay, let's read through this first, because we've only got like 10 minutes. Okay, before we look through this, let's look at this. So to find the equation of the asymptote, you divide the smaller denominator into the larger numerator. So because fractions mean divide, don't they? So if you divide this by this, the answer will be the equation of your asymptote, which is craziness.
So crazy.
The graph will have an asymptote that is a curve of the degree of difference. So see, what is the difference in the degrees between these two? 1, because it's 2 and 1. So that's why its asymptote is a linear. It's a degree of 1. If it was an x cubed over an x, what would be the degree of difference? 2. So the asymptote would be a quadratic.
Wait, what? What? Wouldn't it be 1? Because 1 x to the power 1 x to the power 2 is that a 1 different?
If it was a cubic, yeah.
Oh, a cubic is linear.
Yeah, yeah.
That'll be 2.
Oh, well, I'll go into the polynomial long division in a bit. We won't go hit that just yet. So but oh, this is because of the answer here. But I haven't talked you through polynomial long division yet. So we'll just talk about what kind of answer you're expecting to begin with. So here, the asymptote equation should have a degree that's equal to the difference in the degrees between the numerator and denominator. So
okay.
yeah, so if we have a quadratic over a linear, the degree of difference is 1, because going from 2 to 1, there's a degree of difference of 1. So that's why the degree of the asymptote's 1. Whereas if you had a cubic over a linear, what's the degree of difference again?
2.
2. So you would expect a quadratic
So you just subtract
asymptote.
them.
Oh, just to work out what the degree of the asymptote is, not what the equation is. Yeah. Yeah, just to work out what the degree of the asymptote is. Yeah, like 3 minus 1.
The degree, and then that would mean like it's x.
Yeah. So if you had a quintic over a cubic, what's the degree of difference?
A quintic, like
Yeah.
5?
Yeah, 5.
2.
2, yep. So it'd be a parabola, your asymptote. Pretty weird. Okay, so now the graph will have an asymptote that's the degree of difference between them. So basically a linear or a quadratic. So the asymptote is linear. So this is a linear asymptote, but it's not horizontal. It's just a linear one going up like that. Like, going zhunk. If the difference is 2, the asymptote is parabolic and so on. Okay, so I'm going to talk you through how we did this polynomial long division. So it's going to rock your world. So we did basically the same thing as fractions. You do the top divide by the bottom. So numerator divide by the denominator. So numerator in here, denominator here. And then what you think about is, how many times does x go into x squared?
Once.
X times.
Yes. Yeah, x times, yeah. It was a weird question, wasn't it? How many times does x go into x squared?
X times.
X times, yep. And with the,
Because like 2 gets into 10 5 times, and 2 times 2, x into x squared, x times x times x is x squared.
and then what we do is, what goes here is, we work out what the remainder is. So work out the remainder. What we've said, okay, that goes into that x times, but x times this, what is x times that?
X squared.
Yep.
What is x
Let's
times
do it.
what?
Yeah, x times this.
Can we do it?
No. Yeah, we will. But I'll talk you through this one first. Because let's not get off this too much while we're here. So x times that becomes x squared plus 2x.
Yeah, I get that.
Now here's the remainder.
We should get the negative 1.
Wait, Miss Molly, where did you get the second line from? What happened?
That times that.
Why are
You
you
have to.
timesing
Good to work out the remainder.
Even what?
What?
Why can't? What?
Where'd you get the negative 2 from?
No. I don't even know.
Oh, that hasn't been worked out yet.
Oh, okay.
Yeah, we're not there yet. Yeah, hasn't been worked out yet.
You do. I don't know. You do the numerator in the inside and the denominator on the outside.
Yeah, that's right.
And then you do how many times does what go into what?
X going to that.
Why can't you do 2 going to 1? There's just half.
You won't get the answer.
Okay.
Just that.
It's the x's, and then you put it up there.
Yeah, but then like this whole thing doesn't go into that exactly x times. No, you're right. So this is a method of working out the remainder. So this is kind of the remainder here.
So x
That's our
squared
remainder.
plus 2x is x. How did you get x squared?
Yeah.
That times that.
Okay, got you.
If this did go perfectly into that many times, then that times that would have been the
Whatever number you decide to put on first the top, you multiply by the denominator, and then
we subtract. That minus that is gone. What's minus 1? And then minus 1 minus 2x. Because you do this line, minus that line. So we're minusing all of that.
So x squared minus 1 minus x squared plus 2x.
Yeah. So that's how we ended up with
Wait,
minus
probably
1 minus 2x minus 1.
Miss Malaya, I really think you should do normal long division.
I think
And to be honest, this is kind of different to normal long division anyway. Like so, because the fact you've got 2 things going out. Like normally long division you just have a number out to the left, but now we've got 2 things out to the left. a bit more complicated. I'll do another example with you, but I'll just talk about this one.
You just want
Wait,
to get it done, like,
wait,
to
wait,
make
wait.
it question.
What?
Yeah, no.
Are you subtracting?
We did that one, the top x squared minus 1,
I thought you just
minus
told me
that.
that we had to figure it out so it's minus. Wait, okay.
I think you should just
Minus 2, we haven't worked out yet. Okay, so when we do that, minus that, we get minus 2x minus 1. So, how many times does x, this thing again, x go into minus 2x?
2 minus
Yeah, minus 2, that's where the minus 2 came from. Now we've got to work out the remainder which got cut off. Minus 2 times 2x plus 2 is minus 2x minus 4. Yeah. And then so again we're subtracting. We're doing that minus that, like elimination, simultaneous equation. Elimination.
Where did the negative
I'm almost there, I'm just going to finish it. So that minus 2x minus minus 2x cancels out. And minus 1 minus minus 4 is 3. We don't use this remainder here, but this is the asymptote. See, that's our asymptote equation. Where did we get that from? That's the answer. This is the answer to the long division. So a little thing is, so Grace, if you took that yellow thing and you multiplied it by x plus 2, you'll get x squared minus 1.
Well, we never figured out the minus 2 part.
Yes, you did.
What minus 2?
When?
Yeah, we did.
Negative 2x.
Yeah. Every time 2x minus 2x. We'll do another example as a walk-off next lesson. So we'll do a new one. That's plenty for today.